So first of all, we have to do a bit of analysis. If you remember from our previous class, the analog signal we studied was 0.85 raised to the power of t. For generating it, we used the NumPy library from Python and created our number array from 0 to 11. Now, we know from our earlier lectures that NumPy's range function goes from 0 up to 10 because it does not include the last number. So to generate the signal, we only get values from 0 to 10. Here we are plotting the signal, and all these steps have already been covered in our previous lectures on plotting and visualization. We have already learned how to set figure sizes, how to set supertitles, how to use styles, what parameters are needed, and how to plot signals against time. So let's take a look. This is our analog signal, and you can see that it is the same signal we studied earlier. Its fixed value or coefficient is 0.85. You can see that on the x-axis, we have the time values from 0 to 10, and on the y-axis, we have the amplitude ranging from 0.1 to 1. Now, the next step is to sample this signal and produce a discrete sequence. From our previous discussions, we know that for sampling, the first step is to select a sampling frequency so that we can calculate the sampling interval. For simplicity, let us assume that both the sampling frequency and the time interval are equal to 1. In the sample domain, the sampling interval is represented by a small n. All these steps are the same as before, except this time we use one new step, which is the plt.stem command. Basically, if you remember, in a discrete signal, we do not have a continuous line plot. Instead, we represent values using stems at discrete points. This plt.stem command is new, and we did not discuss it in our earlier lectures. So the priority here is to plot the discrete signal x against n. We also set the line width of the stem segments. Everything else in the code remains the same. Now, let's run the code and see the result. You can now see that both the analog and the sampled signals are shown on the screen. The smooth curve represents the analog signal, and the vertical stems represent the discrete signal. This is our continuous signal, and these are our samples taken at n equals 0, 1, 2, 3, 4, 5, 6, and 7. You can observe that the samples are taken at regular intervals. Suppose I want to find the value of the discrete signal at 1.5. It is not possible because there is no sample at that point. However, if I want to calculate the value of the continuous signal at 1.5, it exists because the continuous signal has values at every instant of time. This shows that the continuous signal exists at every point between 1 and 2, but the discrete signal only exists at fixed intervals such as 1, 2, 3, and so on. So, we have performed sampling very simply by converting this analog signal into discrete samples. From the previous lecture, we know that the next step in analog to digital conversion is quantization. The problem here is that in our discrete signal, the value at n equals 0 is 1. The value at n equals 1 is about 0.85. And at n equals 2, the value is a little below that. However, in quantization, we cannot allow arbitrary amplitude values because the quantization levels are fixed, such as 0.1, 0.2, and so on. So if the value of the discrete signal is 0.211235, we have to round it to the nearest level, which could be 0.2. To do that, we must generate quantization levels in the same way we discussed before. Now, let's run this code cell and observe the quantization levels. Then we will discuss the details. You can see that this is the quantized signal. Here, we have adjusted the values according to the quantization levels. You can clearly see the red horizontal lines representing the quantization thresholds. These lines indicate the amplitude levels allowed in the quantized signal. The difference between this plot and the earlier one is shown by these red horizontal lines. These lines mean that in the quantized signal, only the amplitude values that fall on or near these levels are accepted. For example, if the amplitude of a discrete signal is between 0.8 and 0.9, it will be rounded to either 0.8 or 0.9 depending on which is closer. Similarly, if a sample has a value between 0.7 and 0.8, it will be rounded to 0.7. Now, let's look at the code that generated these results. These are the new lines of code that produce the 10 quantization levels. Everything else in the code is the same as before. The red horizontal lines are drawn at specific positions on the y-axis. For example, the first horizontal line is at y equals 0.1. It starts from x equals 0 and ends at x equals 10. So we have defined it as starting from 0 and extending to 10 on the x-axis, while its y value remains fixed at 0.1. Similarly, the second quantization level is at y equals 0.2, the next one at 0.3, and so on. The color of these lines is red, and they all span the same x-axis range from 0 to 10, but their y-axis values differ according to their quantization level. Now, this is our discrete signal, and we are converting it into a quantized signal. In Python, we are using a very simple and useful function, which is numpy.around of x. When we run this command, we get the quantized values. These are the values of the discrete signal when n equals 0, 1, 2, 3, 4, and so on. For example, when n equals 2, the discrete value might be 0.72. After quantization, this value becomes 0.7. By using the numpy.around function, we are converting each discrete value into its quantized form according to the quantization levels we defined earlier. If we check the code output, we can confirm that when n equals 2, the discrete value was approximately 0.72, and the quantized value is 0.7, which matches the red horizontal level in the plot. In this way, we can confirm any value at any discrete point by comparing the discrete and quantized results. The final step of this lecture is to plot the quantized signal. You can see here that the discrete signal, which was previously represented by blue stems, is now shown with quantized levels. Each stem now aligns exactly with one of the quantization levels, such as 0.9, 0.8, or 0.7. There are no values between these levels because all amplitudes have been rounded. So this is our quantized signal shown in blue, while the red lines represent the quantization levels. By using these levels, we have successfully transformed the discrete signal into a quantized one. This concludes our discussion on analog to digital conversion, which we studied in detail in the previous lecture. Now, we have seen how to implement it step by step using Python.